Hello, today we are going to present our final project of Group 3. The principal purpose of this project was to design and simulate a centrifugal pump with a proposed impeller and voltage geometry, following Grunfos specifications and Gulich nomenclature. Centrifugal pumps are widely used in diverse industries such as food, cosmetics, pharmaceutical, chemical, and hydrocarbons due to their adaptability and essential on water treatment and tank filling. They work by means of rotating blades in a casing that, when rotating, impart kinetic energy to the fluid, increasing its pressure. Due to their relevance, it is crucial to monitor their performance under different conditions through operating curves.
The first part of the project consisted of understanding the theory and the computer-aided design software. A geometry had to be made so that it could be imported to the CFD. Next, important faces and interfaces of the geometry were named, the model was defined, and so were the boundary conditions. Finally, the pump was simulated with different flows. The programs employed for this project were Excel, Inventor, Star CCM, Spider, and MATLAB.
Centrifugal pumps are the most economical and most common pumps used for pumping water in industrial applications, and they're important because pumping systems account for 20% of the world's electrical energy demand, and small improvements could cause a significant decrease of energy consumption and carbon footprint, taking into account that they are available in most developing countries. Centrifugal pumps are better suited for low viscosities because if the fluid is too viscous, the pump will not provide the desired flow pressure outcome, and this may increase losses and therefore decrease efficiency. Cavitation, the formation of vapor bubbles within a liquid in a centrifugal pump, can cause deterioration of the hydraulic performance and damage the pump by erosion and structure vibration. On the other hand, computational fluid dynamics is the science of solving fluid flow equations numerically, advancing the solution through space or time, and is now used in many applications. Likewise, computer aided design refers to any design activity that uses a computer to create or modify engineering designs and can simulate and optimize complex systems. These both can be used to simulate and optimize complex engineering systems. For the geometry design, we took into account the data reported in the manufacturer's curve using water as the fluid with a BEP efficiency of 73.8%, a flow rate of 182 cubic meters per hour, and a height of 120.6 meters. These data were taken as the basis for the pump design, which will be explained as follows. For the design geometry restrictions such as suction and discharge diameter and impeller external diameter were taken into account as shown in Table 1. Operational restrictions of density, viscosity, and operating temperature of the fluids were also taken into account as shown in Table 2. And some of the most important parameters for the creation of the impeller are shown in Table 3, such as number of blades, external and internal diameters, and thickness.
In the drawing section, we can see the top and side view for the impeller, with the dimensions in millimeters, highlighting that it has a diameter of 308, a height of 46.5, an inlet diameter of 135.35, and an outlet height of 19.22. On the other hand, the bolo has a total height of 232.6, with a suction diameter of 80 and a discharge diameter of 65, while the internal cavity for the impeller has a radius of 312. Finally, we can see the drawing for the two pieces together with the previously mentioned information, highlighting the size clearance of 3 millimeters.
The fluid assumptions of the model listed on the left are the ones used in the CFD simulation with the star CCM, being the most relevant to mention the constant density, the gravity, the liquid fluid, the steady state, and the turbulent fluid. With respect to the latter, it was determined that whether the fluids, water and oil, had turbulent behavior using the equations of the Reynolds number showed here, and considering that for turbo machines, if the value of the Reynolds number is greater than 2 times 10 to the fifth, it is considered as turbulent flow. For both water and oil, they gave turbulent flow with calculated values of 2.96 times 10 to the 7th and 7.98 times 10 to the 5th, respectively.
Three meshes were simulated, a standard of 1.2 million cells, a thick with a 30% decrease in number of cells, and a fine with a 30% increase. The values for total head and efficiency with the respective error for the three meshes can be seen in the table. The computational time for each mesh was also calculated. These values were compared to the reported total head and efficiency. The figure on the left, which was adapted to resemble the Valdez diagram, shows that the thick mesh has a slightly higher error than the standard mesh, but has a much lower computational time. Furthermore, the efficiency value for the thick mesh was closer to the manufacturer's efficiency. For these reasons, all CFD simulations were analyzed using the thick mesh. Here, we present some important phases and interfaces, like the inlet, outlet, cutwater, and impeller, along with a detailed view of the mesh quality. 10 to 15 points were evaluated for each fluid to create the following figures. The system is more efficient with water as indicated by the higher efficiency values for the same flow rates in the left figure. Additionally, the best efficiency points for water and oil are both higher than the manufacturer's BEP, which indicates that the system was originally designed for lower flow rates and that the fluid's characteristics, such as density and viscosity, impact the performance significantly. On the right, a comparison of the total head versus flow rate is shown. Both the water and oil deviate from the manufacturer's data. The reason for this is that the geometry was calculated using the manufacturer's BEP, but once the pump was simulated, it was visible that this was not the actual best efficiency point. For a more accurate representation, a new geometry should be designed using the new BEP flow rates. Since the pump would now be working with higher flow rates, it would now be considered a mixed flow pump. This means that the fluid enters axially but exits diagonally, that is, with an angle.
In the first part, we can look at the results of the impeller speed profile, which was evaluated at 5 different points: shut-off, intermediate point, manufacturer BEP, free delivery, and design BEP. All of them had a range of speed between 1 and 49 meters per second. It can be observed that the changes between the different points aren't noticed enough. This could be due to the mistakes in the start design, specifically in the geometry part, when we needed to separate the parts of the impeller. Although theoretically the values are similar to each other, they should vary a little. Also, we can analyze that the speed is greater towards the ends of the impeller due to the centrifugal forces, since the fluid particles need to travel at a larger radius, increasing their speed as they move away from the center. The cavitation profile was performed. This phenomenon occurs when the fluid pressure is lower than the vapor pressure of the same, causing bubbles, which is indicated in our different cases for the pump since the yellow color is in most part of the pump. It is expected for future occasions to focus more on geometry since this influences the pressure distribution and speed of a fluid. If it is not designed up properly, these low pressure zones can occur. The same thing happens in the wall G plus profile where the same points were evaluated and the mistakes done were mentioned above. The results were very similar to each other. It can be observed that the color bar was between a range of 0.08 and 140.8. However, all the results are below 5, where the blue and the green coloring indicated, which is correct based on the theory to ensure that the first layer of the cells in the mesh is within the laminar sublayer of the flow boundary layer, since it can be observed that the minimum value is 0.38 and the maximum is 2.37.
This is the vector seen for both water and oil at the BEP flow. The direction is counterclockwise, meaning that the fluid moves in the direction of the discharge. Therefore, the simulation was designed correctly.
In conclusion, the objective of the project was successfully achieved as the centrifugal pump was efficiently modeled using both CAD for the design and CFD for the performance analysis. The simulation confirmed the inverse relationship between fluid viscosity and pump efficiency noted in the literature, as the pump showed higher efficiency with the water than with the oil. A thick mesh independent model was determined to be the most suited for balancing time and efficiency in the simulations. Additionally, various dimensional numbers such as the Reynolds number were calculated to ensure accurate representation of the simulation models.
Continuing concluding, the design is dependent on the best efficiency point. To obtain the most accurate simulation, the design has to be repeated as many times as necessary, where the effectiveness is visible with the curve of head versus flow. And the last one, mesh sense for important phases and interfaces were illustrated successfully. Also, velocity cavitation and G plus sense were generated. However, the results were not as expected in the last sense because the change was minimal, not showing the effect of the flow. The geometry would necessarily need to be fixed for further analysis.